Good morning. This week we have one lesson on a type of mathematics called graph theory. And the idea is often when we analyze theoretical problems, it's useful to change the problem into a problem which involves a collection of vertices joined by lines. Graph theory was started by Leonard Euler when he visited a city called Konigsberg in 1736, and he was set a problem by the people living in this city. In this city, there were 4 land masses which were joined together by 7 bridges. And the problem which the locals often asked visitors was, can a person walk around the town and cross each bridge once and only once? Leonard Euler was the first person to solve this problem. And what he did was he looked at a map of the city and he realized we don't need to know where the buildings are, we don't need to know where the roads are or the shape of the rivers. All we need to know are that there are 4 land masses and that they are connected together in a particular way with bridges. So Leonard Euler realized that instead of looking at the map on the left, he could simplify the problem to the picture on the right. These 4 blue circles represent the land masses, the pieces of land in the city, and the red lines represent the bridges. This type of mathematics, called graph theory, like lots of types of mathematics, when it was started, it was just considered an interesting piece of mathematics, something which could be used to solve some puzzles. But many years later, it has practical applications. It's used in computing, in physics, in neurology, in chemistry, and many other disciplines. Let's make a start on the definitions. A graph is formed by a collection of points, which are called vertices, and lines, which are called edges. For vertices, we use lowercase letters, for example, A, B, C, etc. And for an edge, which joins a vertex U to a vertex V, we write this as E is equal to open bracket, U comma V close bracket. U and V, the vertices or the points U and V, are called the endpoints of the edge E. A non-empty set of vertices together with a set of edges, which may or may not be empty, is called a graph. An edge which starts and finishes at the same vertex is called a loop. Here's an example of a graph. This graph has 3 vertices. These are the 3 blue circles, and it has 4 edges, 4 red lines. Note that the edge at the bottom right starts and finishes at the same vertex. So this edge is called a loop. For example, let V, the set of vertices, contain 4 points, A, B, C, and D, and let E, the set of edges, contain 5 edges, E1, 2, 3, 4, and 5. And we're told that edge number 1 goes from A to B, edge number 2 goes from B to C, etc. And the problem we're asked is draw this graph. The first thing to do is to draw the vertices, A, B, C, and D. If we want to, we could draw them like this. Maybe we want to do this a different way. Perhaps we swap C and D around. Maybe we draw the points in a line. Maybe we draw them like this. These are all correct. It's up to you to decide it's completely up to you to decide where you draw your vertices. I'm going to write them like this, A, B, C, and D in a square. And then I want to draw the edges. Edge number 1 joins A to B. Here we are, this is edge number 1. And then edge number 2 joins B to C. Edge 3 joins C to D. Edge 4 joins A to C. And edge 5 joins B to D. And then we're finished. This is the answer to this example. Two edges which have the same endpoints are called parallel edges. Now let's run through some types of graph. First of all, a simple graph is a graph which does not have parallel edges or loops. This graph is not a simple graph. This graph has parallel edges. These two edges on the right both go from B to C, or equivalently from C to B. So these are parallel edges. If a graph contains parallel edges, it is called a multigraph. A pseudograph is a non-simple graph in which both loops and parallel edges are permitted. If E is an edge of a graph like this, then we say that the vertices U and V are neighbors. In this picture, A and B are neighbors, but A and V are not neighbors because there is not an edge from A to V. The degree of a vertex in a graph such as these is the number of edges connected to the vertex V. When we calculate the degree of a vertex, for each loop we count this as 2 edges. For example, look at this graph. Give the degrees of all the vertices in this graph. First, I want to look at A. A has 2 edges. Here's 1 and here's 2. So the degree of A is 2. Next, look at B. Count the number of edges connected to B. 1, 2, 3, 4. The degree of B is 4. The degree of C is 4. The degree of D is 1. The degree of E is 3. The degree of F is 4. And the degree of G is 0 because G does not have any edges connected to it. Another example. Give the degrees of all the vertices in this graph. We look at A and we count 1, 2, 3. We look at B. B has a loop. We count a loop as 2. So 1, 2 for the loop, and then 3, 4, 5, 6. The degree of C is 1. The degree of D is 5, and the degree of E is also 5. A vertex which does not have an edge, or in other words has degree 0, is called an isolated vertex. In this picture, the vertex G is an isolated vertex. A vertex of degree 1 is called a pendant. In this picture, vertex D is a pendant because D has only one edge. Our first theorem from today. Let's suppose G is a pseudograph and let NE be the number of edges in G. Then NE, the number of edges, is a half multiplied by the sum of all of the degrees of the vertices. For example, a graph has 10 vertices. Each vertex has degree 4. How many edges does this graph have? Let's suppose these vertices are called V1 up to V10. Then, by the theorem on the previous page, we can calculate that the number of edges is a half multiplied by the sum from 1 to 10 of the degree of Vi. We have a half multiplied by 4 plus 4 plus 4 plus 4, etc. And we can calculate that this is equal to 20. Therefore, this graph has 20 edges. We might like to have a graph where the edges have directions. Instead of just a line joining two vertices, perhaps we use an arrow to denote the direction of that edge. Such a graph is called a directed graph or a digraph. If a directed graph has parallel edges, it's called a directed multigraph. In a graph, all of the edges are the same type. So either we have an undirected graph where all of the edges are just lines, or we have a directed graph where all of the edges are arrows. Let's suppose we have a directed graph. Then if we write an edge E is equal to open bracket U comma V close bracket, then it's important whether if we put U on the left or if we put U on the right. This edge starts at U and it finishes at V. We have U and V. The arrow should start at U and should go to V. Again, let's suppose we have a directed graph. Then we can talk about an in degree and an out degree of a vertex V. The in degree, which is degree subscript minus, is the number of edges coming into V, and the out degree, or degree superscript plus, is the number of edges coming out of V. If we have a loop, we count this as 1 for both the in degree and the out degree. For example, look at this graph. Find the in degree and out degree of each vertex in this graph. Let's do the in degrees first. Look at A. How many arrows are going into A? Just counting the arrows which go into A, we have 2 arrows pointing into A. So the in degree of A will be 2. For B, we have 2 arrows going in. The in degree of B will be 2. The in degree of C will be 3 because there are 3 arrows going into C. The in degree of D will be 2, the in degree of E is 3, and the in degree of F is 0. Next, out degrees. How many arrows are coming out of A? We can count 1, 2, 3, 4 arrows are coming out of A. So the out degree of A must be 4. The out degree of B is 1. The out degree of C is 2. The out degree of D is 2. The out degree of E is 3. And the out degree of F is 0. Before we go on, let me count the number of edges in this graph. There's the loop at the top left. This big one is 2, another loop is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This graph has 12 edges. Next, I want to add up the indegrees. Indegree of A is 2, indegree of B is 2, and so on. So 2 plus 2 plus 3 plus 2 plus 3 plus 0 is also 12. And we can add up the out degrees. 4 plus 1 plus 2 plus 2 plus 3 is also 12. In fact, this is always true. If we have a directed graph, then the number of edges in the graph is equal to the sum of the indegrees, and it's equal to the sum of the out degrees. This is because every edge starts at a vertex, so it's counted once for each indegree. It's counted once every time we count indegrees, and every edge finishes at a vertex, so we count it once every time we add up the out degrees. A simple graph which includes all possible edges is called a complete graph. A complete graph which has n vertices is denoted as k subscript n. Because each vertex in Kn is connected to all of the other n-1 vertices, Kn has n multiplied by n-1 over 2 edges. Some examples, the first 6 complete graphs. K1, just a point, 1 vertex and no edges. K2 has 2 vertices and therefore 1 edge joining them together. K3 is a triangle, 3 vertices and all of the possible edges that we can draw without drawing parallel edges. K4, K5, K6, and then we could do etc., etc. if we wanted to. A planar graph is a graph which can be drawn in the plane in such a way that its edges intersect only at their endpoints. For example, this graph, you can see in the middle, the edges are intersecting at a point which is not a vertex. But in fact, this is a planar graph because we could move the vertices and the edges around in such a way that the edges do not cross or intersect each other. Therefore, this graph is a planar graph. A graph which is not a planar graph and therefore can only be drawn without intersecting edges in three-dimensional space is called a three-dimensional graph. For example, this graph is not a planar graph. Try to draw it so we can imagine this existing in three-dimensional space where the edge from A to C is somehow above the edge from B to E. You can look at this graph and you can convince yourself that it's not possible to rearrange this graph in such a way that the edges do not intersect. We also have graphs which are called cycle graphs. If we have n vertices and each edge joins a vertex to the next one in a loop like these are called cycle graphs. If we take a cycle graph and we add an extra point in the middle, an extra vertex in the middle, and then connect that vertex to all of the other ones, then we have a wheel graph. These are the first 4 wheel graphs. You'll notice that the notation is a little unusual here. W3 doesn't have 3 vertices, it has 4 vertices. And the reason is that W3 looks like C3, but with 1 extra vertex. Likewise, W5 looks like a cycle graph C5, but with 1 extra vertex in the middle. A bipartite graph is a graph where the set of vertices can be divided into 2 distinct subsets, let's say V1 and V2, such that every edge connects a vertex in V1 with a vertex in V2. What this means is there are no edges which go from points in V1 to V1, or no edges which go from points in V2 to V2. For example, this graph, C6, previously I drew this as a hexagon, but it doesn't matter where we draw the points. We might choose to draw C6 like this. Then we could divide the vertices into 2 sets. We could put V1, V2 and V3 using this notation in a green set, and V4, V5, V6 in an orange set. Then you'll notice that every edge goes from the green set to the orange set. There are no edges which join a vertex in the green set with another vertex in the green set. There are no vertices which draw a vertex in the orange set with another vertex in the orange set. Therefore, this graph is bipartite. Look at this graph. Is this graph bipartite? Can we separate the vertices into 2 sets or 2 colors such that no edge joins 2 vertices of the same set or the same color? Let me show you how to answer this problem. We're going to answer this problem using 2 different colored pens. First, we pick a pen and we pick a vertex. It doesn't matter which vertex we choose. Let's just suppose that I'm choosing vertex B and I'm choosing to color vertex B in orange. Then I switch to my other color. Let's suppose my second color is green. I want to color every vertex which is connected to B using my green pen. First of all, B is connected to C, so I'm coloring C in green. B is also connected to E, so I'm coloring E green. And B is connected to F, so I color F green. Then I switched back to my orange pen. Every vertex which is connected to green vertex, I want to color orange. For example, A and D are connected to a green vertex, so I color them orange. G is not connected to a green vertex, so we leave that one. Switch back to the green pen and color G in green. Every vertex has been colored in. None of the orange vertices are connected to each other. None of the green vertices are connected to each other. Therefore, this graph is bipartite. Let's do another one. Is this graph bipartite? Choose a vertex, any vertex, it doesn't matter which one we start with. Let's suppose I'm starting with D, and let's suppose I'm choosing to color in D using my green pen. Then I switch to my orange pen, and I color in every vertex which is connected to D. Now, you should note that there's a problem here, look. E and F are connected together, but E and F are both orange. This tells us that this graph is not bipartite. Our next idea is the idea of walks. What is a walk? A walk is a list of vertex, edge, vertex, edge, vertex, edge, etc., ending in a vertex. The first one in the list is a vertex, the second one is an edge, the third one is a vertex, then an edge, then a vertex, then an edge, etc., etc. And the rule is that each edge must connect the vertices that it's between. So edge 1 must connect to vertex 0 with vertex 1, edge 2 must connect vertex 1 with vertex 2, etc., etc. For example, this is a graph. Let's suppose I want to make a walk. Suppose I start at A, I walk from A to B, then from B to E, following the green arrows, from E to D, to C, to F, to G, and then back to F. We can write this as A, because I'm starting at A, E1, B, because I use edge E1 to go to B, and then E5, E, because I use E5 to go to E, etc. And this walk ends with F, because I finished at F. An Eulerian trail is a walk which satisfies two rules. No edge is repeated, and every edge is included in the walk. For example, I'm saying that this walk, D, E5, E, E6, A, E7, F, E8, B, E1, A, E4, D, E3, C, E10, G, E9, B, E2, C, is an Eulerian trail. Let's check this. The walk starts at D, it goes to E, and then it goes to A, then to F, then to B, then to A, and then to D, then to C, to G, then to B, and then to C. We've used every edge once and only once in this list, so this is an Eulerian trail. The Konigsberg bridge problem, which we saw at the start of this lecture, which said, is it possible to walk around Konigsberg and cross each bridge once and only once? We can rephrase this as, does there exist an Eulerian trail in Konigsberg? We're not ready to answer this question yet, but we will soon. Graph is called connected if there exists a walk between every pair of vertices. For example, in these two graphs, the bottom graph is connected Doesn't matter where we start and where we want to finish, it's possible to walk along the edges. For example, if I start at D and I want to get to A, this is possible. If I start at C and I want to get to E, again, this is possible. The graph at the top is not connected. If I start at G and I want to get to A, it's not possible to walk from G to A. The top graph is not connected. Theorem. Let's suppose we have a connected graph. Then there exists an Eulerian trail if and only if the number of vertices of odd degree is either 0 or 2. In other words, either every vertex has even degree, or 2 of the vertices have odd degree and every other vertex has even degree. Furthermore, if there are 2 vertices of odd degree, then the Eulerian trail must start and finish at these 2 vertices. For example, let's look at the complete graphs. First of all, for graph K3, every vertex has degree 2. Therefore, there is an Eulerian trail in K3. If we look at K5, the degree of every vertex is 4, because every vertex has even degree. There exists an Eulerian trail in K5. However, if we look at K4, the degree of every vertex is 3. There are 4 vertices of odd degree. Therefore, K4 does not contain an Eulerian trail. Go back to this one, which we looked at previously. We've already found an Eulerian trail in this graph. We can count the degrees of the vertices. The degree of A is 4, the degree of B is 4, the degree of C is 3, the degree of D is 3, and the degrees of E, F, and G are 2. 2 of these vertices have odd degree, that's C and D. So there exists an Eulerian trail, and our trail must start and finish at the vertices C and D. Now we can answer the famous Konigsberg bridge problem. Does there exist an Eulerian trail in Konigsberg? To answer this, we calculate the degrees of the vertices. The degree of A is 3, the degree of B is 5, the degree of C is 3, and the degree of D is 3. We have 4 vertices of odd degree. Therefore, the answer is no. There does not exist an Eulerian trail in Konigsberg. It's not possible to walk around. It was not possible to walk around the city and cross each bridge once and only once. The final idea for today's lesson is the idea of Euler's formula for polyhedra. Euler's formula is the number of vertices minus the number of edges plus the number of faces on a polyhedra. Let's do some examples. Let's start with a cube. How many vertices does a cube have? There's 1, 2, 3, 4 on the top and another 4 on the bottom, so there must be 8 vertices. How many edges? 4 on the top, must be another 4 on the bottom, that makes 8, and then 4 vertical edges. In total there are 12. And how many faces on a cube? We know this, a cube has 6 faces. Euler's formula is the number of vertices minus the number of edges plus the number of faces. That's 8 minus 12 plus 6, which is equal to 2. Another example. Let's look at a tetrahedron. This object has 4 faces and each face is a triangle. There are 4 vertices, 6 edges and 4 faces. We can calculate Euler's formula, 4 minus 6 plus 4, and again 2. Another shape. Let's look at a pyramid. A pyramid has 1 vertex on the top and 4 on the bottom, so 5 vertices. 8 edges, 4 on the bottom and then 4 joining the top vertex. And it has 5 faces. We can calculate Euler's formula. 5 minus 8 plus 5 is, that's 2 again. We've done 3 objects and all 3 times we've got the number 2. A dodecahedron. A 12-sided shape. Deca means 10 and do means 2, so it's 2 plus 10 sides. A dodecahedron has 20 vertices, 30 edges and 12 faces. We can calculate Euler's formula. 20 minus 30 plus 12 is, it's 2. Let's do one more. Let's see if we get 2 again. Let's look at this shape, which I'm calling a football. This shape is made of 12 pentagons and 20 hexagons. How many vertices? We can calculate this. Every vertex is on a pyramid. So every vertex is on a pentagram. We have 12 pentagrams, and each pentagram contains 5 vertices. So there must be 12 multiplied by 30 vertices. How many edges? Every edge joins together 2 vertices, and every vertex has 3 edges. So we can calculate 60 vertices. Each vertex has 3 edges, but then we're counting each one twice. So 60 multiplied by 3 divided by 2, which gives 90 edges. And the number of faces, we have 12 pentagrams plus 20 hexagrams. So for faces, we would just do 12 plus 20 to get 32. And then we calculate Euler's formula. 60 minus 90 plus 32. And what do we have? We have number 2 again. Is it always 2? And if it is always 2, how could we prove that it's always 2? We just know we're doing polyhedras without holes in. We don't have something with a hole in the middle. we have a holeless polyhedron. Let me explain how we would prove that this is true. Let's start with the cube as our first example. 8 vertices, 12 edges, and 6 faces, remember. What we're going to do is we're going to take this cube and we're going to remove the top, and we're going to throw the top away. And then we're going to stretch and squash the cube, and we're going to squash it down flat, like this. Then we have a two-dimensional picture with vertices, edges, and faces. In other words, we have something which looks like a graph. This graph has edge vertices, 8 vertices. Remember, we haven't done anything to change the number of vertices. It also has 12 edges because we haven't done anything to change the number of edges. We can calculate the faces, 1, 2, 3, 4, 5, inside the graph. But remember, we took the top off and we threw the top away. To count for the face that we threw away, we also calculate all of this. We count all of the space outside of the graph, and we call this the 6th face. Tetrahedron, we could do the same thing. Remove one face, throw it away, squash the tetrahedron flat, and then count the number of vertices, the number of edges, and the number of faces, but including all of the outside as the 4th face. Each one of these pictures has 4 vertices, 6 edges, and 4 faces. We could do the pyramid. Remove, let's say, the bottom of the pyramid, squash it flat, and then count the outside as a face. Or we might do some irregular shape like this capital T. Both of these pictures, the 3-dimensional T on the left and the graph on the right, have 16 vertices, 24 edges, and 10 faces. We could say that every 3-dimensional polyhedra, which doesn't have a hole in it, is equivalent to a connected planar simple graph. That means if we know something about graphs like this, we know that it's true for polyhedra. This is something we do in maths a lot. If we want to understand one problem, we change it into a different problem, and then we show that the 2 problems are equivalent. If we can prove something about the easier problem, then we also know that it's true for the other problem. Now, what do we know about connected planar simple graphs? Let's start with the easiest one, the first complete graph. K1, which is also called the trivial graph, has 1 vertex, 0 edges, and 1 face. And we can calculate Euler's formula for the trivial graph. Number of vertices minus the number of edges plus the number of faces is 2. Remember, this is 2 for the trivial graph. Next, let's just take any connected planar simple graph. Any graph that you can draw, just draw some vertices on a piece of paper, draw some edges connecting them. As long as it's a connected graph and it's a planar graph and it's a simple graph. For example, I've drawn this one. Just drew some vertices, I've just drawn some edges. There are no loops, there are no parallel edges, none of the edges intersect, and all of the vertices are connected to each other somehow. And then we could ask, how can we simplify such a graph? First thing we might want to do is we might want to remove a pendant vertex. Let's suppose I cut just here. I'm going to remove one vertex and I'm going to remove one edge. What happens when I do this? I've removed one vertex, so the number of vertices decreases by 1. I've also removed an edge, so the number of edges decreases by 1. The number of faces stays the same. So then when we calculate NV minus NE plus NF, NV becomes minus 1, 1 less. For the number of edges, it's also decreased by 1, but because this is minus the number of edges, that's plus 1. And the number of faces hasn't changed, so plus 0. The change is minus 1 plus 1 plus 0, or 0. There's no change in Euler's formula when we do this. What else could we do? We could also cut an edge which is not connected to a pendant. Let's suppose I cut and remove this edge. Then there will be one less edge, but also there will be one less face because the inside will be now connected to the outside. When we do this, we don't change the number of vertices, so NV stays the same. We remove one edge, so NE decreases by 1, and we also remove one face, so the number of faces decreases by 1. That means Euler's formula stays the same. There's 2 techniques we can use to simplify the graph, and at each step, Euler's formula is not changing. So use these again and again. Let's remove a pendant vertex. Let's remove an edge, and a pendant vertex, etc. Keep simplifying this graph. Remember that each one of these steps, Euler's formula is not changing. And we keep going until we just have one vertex. In other words, we keep going until we end up with a trivial graph. That means that the graph that we started with, which was any graph we could think about, has the same Euler formula as the trivial graph. In other words, if G is a connected planar simple graph, any connected planar simple graph, then Euler's formula must be equal to 2. And the same must also then be true for all polyhedra which don't have holes. Every polyhedra without a hole has Euler formula equal to 2. And that is the end of today's lesson. Next week, we're going to start talking about calculus. We will study limits, continuity, and differentiation. I'm now to answer your questions, but let me preface that by answering what I guess would be the first question. No, I haven't started reading your exams yet. You should expect to wait another 1 or 2 weeks before you get your results.